Hello everyone, my name is Alessandro Trinchera and I would like to present you the work of Halton Arp, an American astronomer and astrophysicist who started his career collaborating with Edwin Hubble. It's the perfect timing to introduce his work as the galaxy M87, to which the picture of the black hole belongs, is ejecting radium and X-ray matter out of its core, maybe the most important thing. We have been having this data and picture for a long time. The mainstream is making business with the picture of the black hole and the expansion of the universe, but the open topics in astronomy and astrophysics are yet to be discussed. Arp worked on determining the distance scale in cosmology and then dedicated his life to the study of quasars and to a new explanation of the stellar redshift. It's only a short introduction before to show you the core of his work. If we mix up his revolutionary observations with different boundary conditions in the general field equations of Albert Einstein, we are able to show a new view of the cosmos, a non-expanding cosmos. I would like to clarify something. First of all, my purpose is to divulgate Halton Arp's work, trying to be as objective and straightforward as I can. I'm basically extracting the most important facts without expressing my personal opinion, but making remarks by inferences. Secondly, he found a few important reasons why the proposed explanations of the cosmic expansion seem to be at least questionable as a result of assumptions. Believe me, it's not science fiction what we are gonna see, but it's really a different scientific approach based on pure observations. In contrast to the large amount of criticism that Halton Arp faced during his lifetime, every opinion is equally important and deserves attention. Our purpose as human beings and scientists accordingly is to join forces, share information and expand the knowledge and understanding of cosmic phenomena. You can check all information contained in this video in the following books: Quasars, Redshifts and Controversies, published in 1987, C.Randall, Redshifts, Cosmology and Academic Science, published in 1998, Catalogue of Discordant Redshift Associations, published in 2015. With this section, I'm starting from the conclusions in order to keep your attention high right from the beginning. High redshift quasars and peculiar galaxies are observed interacting with low redshift galaxies, and since the light time and travel path is identical, then we can state that the objects are at the same distance. Galaxies with low mass are ejected from older ones. As these new galaxies age and grow in mass and size, aggregating matter, they in turn eject new generations in a cascading process. This process, based on observations, is the exact opposite of what claimed by the Big Bang theory, assuming the mathematical expansion of space among intergalactic objects. The universe is not necessarily exploding away from us in all directions, but it gave and has been giving birth to new cosmic objects. Redshifts do not generally indicate recession velocity and are not reliable distance indicators, but rather are related to intrinsic properties. In fact, high redshift objects are often at the same distance and physically associated with galaxies of much lower redshift. The younger the object, the higher is its intrinsic redshift. Since the redshift is an intrinsic property and not a measure of distance, at given redshift the best indication of distance is a faint apparent magnitude of quasars. Cygnus A is a radio galaxy emitting material in opposite directions to conserve momentum and to keep the whole system in equilibrium. NGC 4486 is a supergiant elliptic galaxy ejecting material. First evidence of two-sided material jets were in the optical field, then confirmed by the coincident radio analysis. NGC 5128 is a radio galaxy with an active nucleus emitting strong lobes of radio and X-ray material in opposite directions. Emission lines indicate a shock excited, supporting the conclusion that the jets are the result of the passage of some galactic entity, coming out along the ejection line into regions far away from the galaxy. The presence of oxygen emission line indicates that the gas temperature is greater than expected due to a physical collision. Moreover, as we will see, hydrogen clouds could arise as a consequence of an ejection. If we examine the outer regions of the galaxy M87, we find an elliptical galaxy along its jets. The physical reality of the line gets confirmed by the X-ray objects found along the same line of the elliptical galaxies. Elliptical galaxies have older stars and tend to be in the center of clusters. The slight misalignment of the elliptical galaxies along the ejection line can be explained by the rotation of the central galaxy, or the galaxy themselves have probably undergone ejection phases and created younger galaxies in the vicinity. These successive young generations of galaxies are smaller in dimension, with higher intrinsic redshifts, as we will see. They show in the sky an overall S-shaped distribution, in both directions along the minor axis. Same observations can be done for Centaurus A, with the difference that we find spiral galaxies along its ejection lines instead of elliptical ones. Spiral galaxies are less massive and indicate more recent origin associated with high redshift, and therefore contain younger stars, and they appear preferentially towards cluster edges, because were ejected at a more recent epoch. The ejection creates a differential rotation that turns ejection velocity into rotation velocity at the arms, giving accordingly the characteristic spiral shape. Star formation takes place with density wave compression along the ejected filaments. The tracks of the same ejections mark the birth of the quasar. Let's have a look at the center of our local group, as it appears projected on the sky. Open circles are hydrogen clouds, and the last object at the bottom left is the NGC 598. All the objects lie along a straight line that coincides with the minor axis of the central galaxy NGC 224, or M31, as known as Andromeda Galaxy. The redshifts of all companions are positive with respect to this main galaxy, except the hydrogen clouds that could represent more recent ejections along this line. It's only one of many cases of chain of galaxies that can be found, a backbone of a more general distribution of the galaxies throughout the intergalactic space, where redshifts cannot represent recession velocities. Otherwise, the objects with those velocities would break up and move off the line. Let's have a look at the image shown, and let's observe the distribution of the objects. In all cases, the amazing property is that the brightest lowest redshift galaxy of the region falls in the middle of the strings. Ejections and counter-ejections are physical phenomena operating in the universe. Extragalactic matter in the universe unfolded first from a few centers and then further from secondary and so on. After all, the usual assumptions of conventional astronomy is exactly the filamentary distribution of the matter in the universe. A quasar, quasi-stellar object, conventionally seen as a normal galaxy having a superluminous nuclei, is a radio and X-ray source. It can be found as pairs around active galaxies not at great cosmological distance. Its spectrum is shifted to very high wavelengths, therefore thought at great distance according to its high redshift, due to the assumption that all extragalactic redshifts are caused by velocity and indicate distance. Quasars look like emitted from a closed galaxy, have a tendency to be fainter in luminosity for higher redshift, and are to be found at most around Seyfert galaxies, having a small amount of energy concentrated into its nucleus, from which the quasars are ejected. Seyfert galaxies have been identified as quasar factories. Positional measures by radio telescopes revealed quasars moving up to 10 times the light velocity, violating Einstein's theories. We have to underscore that all measurements and observations concerning quasars are considered nowadays puzzling and altering data which contradict the Big Bang hypothesis. Quasar pairs tend to lie along the minor axis direction of the central galaxy. We mean the spin axis of the galaxy perpendicular to the galactic plane. The most quasars were ejected away from their galaxies of origin, but it's possible that sometimes a galaxy might be caught in the act of ejection. We can have a look at the first instance of two X-ray sources paired across the nucleus of the galaxy NGC 4258. The circular lines represent the X-ray emission. To notice how the spectrum of the two quasars is similar, with the wavelength shifted with respect to each other. Looking at the wonderful picture, it's possible to recognize the central spiral arms towards the east and the west as a result of the quasar ejection. Actually, the arms are not seen in the visible light, but only by radio analysis, showing arms that will form the new spirals. It leads to suggest that they are ejected outward from main bright galaxy and then become the companion galaxy. In other words, quasar may represent the birth of the galaxy. Along the minor axis, the quasars are able to exit because of the path of least resistance. In case of very disrupted galaxies, the quasars tend to be smaller, more numerous and closer to the galaxy of origin, due to the ejection through its main substance, which break up and slow down the material being ejected. Another instance is the two strongest radio sources, redshift .62 and .67, close to the disturbed galaxy IC 1767. The average cone angle around the minor axis for ejected quasars is plus/minus 20 degrees, whereas for companions of parent galaxy is plus/minus 35 degrees, and the height is almost 0.5 megaparsec. A foreground galaxy is often close to background quasars. There might be many lines of quasars crisscrossing through all cosmic regions in space at the present, giving difficulties to identify their ejection origin. NGC 3561 within the galaxy cluster Abel 1185 is the first evident example of a central galaxy and elliptical one caught in the act of ejecting a protogalaxy. The trace left along its path is clearly visible, pointing to the upper part of the picture. We can see the picture at different wavelengths, proving the ejection. UGC 10214 is another beautiful instance of ejection. If an object were falling to the galaxy as thought, it would require an interacting medium to produce the track. So we conclude it was ejected, and ejection destabilized the galaxy, giving a recoil appearance. I showed a picture of this galaxy to friends who have no special interest in astronomy, and I asked what they see in this picture. The answer was an explosion, referred to the galaxy, and ejection referred to the material trace left on the left side. The spiral galaxy NGC 7603 is interacting with a smaller elliptical galaxy nearby. These two galaxies, of different low redshifts, are connected by a matter bridge, where it's possible to see two faint quasar objects with high redshifts. The picture fits with the model where an ejection leads a trail of matter. Going inward to the beginning of the trail, we find increasing redshifts. The highest object has a redshift .391, represents the last ejection in time, whereas the second bigger object with redshift .057 represents the last evolution stage. The redshift is similar to the parent ejecting galaxy. The ejection of the companion galaxy occurred in the plane of the main galaxy, because the interaction with the material caused a break effect of the material ejected, being not too far away from the originating galaxy. NGC 4319 with redshift .006 is connected to a quasar Mark 205 with redshift .07 through an X-ray bridge. As the quasar is in an old evolutionary stage, the arms of the galaxy are coming off and the galaxy is disrupting due to a perturbation, the luminous filament is faint. Even a reduced exposure shows the matter bridge. Zooming into the Markarian 205, the X-ray filaments are visible at the edges on the quasar with redshifts .46 and .64. The scientific debate concerning the position of the quasar having high redshift behind the low redshift galaxy finds here a clean answer. If the quasar were really in the background or inside the galaxy, we should detect absorption lines from the foreground galaxy, but instead any absorption line was found. The quasar is in front of the galaxy in no line of sight. The galaxy 3C 303 emits a radio jet consisting in ionized gas or plasma where the motion of the particles are bent by magnetic lines, causing radiation. The radio filament extends westward through 3 ultraviolet objects and terminates at the quasar. It's a strong evidence for connection of a low redshift galaxy with the quasar. The radio emission is visible in the radio map, confirming the direction of ejection, the trail left behind, and the quasar at the end position. The galaxy NGC 520 reveals 4 radio quasars, all of different redshifts. NGC 3034 is a characteristic galaxy, one of the brightest, revealing a set of emission filaments from either pole, where 3 quasars have been found contained within a cone, emerging from the center of the galaxy. Moreover, a radio source appears to be ejected at the notch of the cone. From this kind of ejection process arise the quasars. The galaxy is actually a companion of the galaxy NGC 3031, from which accordingly could have been ejected in the past. Before to start this section, it's important to define the difference between 2 different types of luminosity that we can encounter. The intrinsic luminosity is the energy output by a galactic object independent from the distance. The apparent brightness or magnitude is the perceived brightness of a galactic object dependent from the distance and from the intrinsic luminosity. We have an inverse square law with the distance and a direct proportionality with intrinsic luminosity. If we are closer to the light source, it will appear brighter, and if we are distant, it will appear fainter according to this law. To notice that, in the scale, the apparent magnitude is greater by smaller values, contrary to the logic. The physical reality of quasars can be described by plotting the apparent magnitude versus the redshifts for different locations in space. High redshift quasars are shown in black, radio quasars are open circles. In the North Galactic Hemisphere, associated with the Virgo cluster, the quasars are concentrated in redshift near to 1, with almost no quasars near 2, in contrast to the opposite direction of the sky in the South Galactic Hemisphere, where the strong concentration is at redshift equal to 2. We have therefore found a violation of the cosmological principle that, on large scale, the distribution of the galactic objects is homogeneous. We can consider, for instance, the NGC 1097 for the North Galactic Hemisphere and the sculptor area for the South Galactic Hemisphere and trace a line satisfying the average values. It turns out that if the quasars were really at their redshift distance, we would expect at least a negative slope line, according to the inverse proportionality between apparent luminosity and distance. We observe instead another correlation. Quasars with redshift 1 must be intrinsically most luminous than quasars at lower or higher redshift. Quasars with redshift 2, instead of being the most luminous objects in the universe, as stated from the Big Bang theory, must actually be the least intrinsically luminous. Let's just have a look at all quasars in the vicinity of the center of the local group, and of the most conspicuous companion galaxy, NGC 598. There is a concentration of quasars following lines on the southeast part of the diagram, rotated with respect to each other. The direction of ejection does not stay fixed in space, because the galaxy rotates in time. This implies that what are now the lower redshift quasars, open circles, were ejected earlier. They had a higher redshift and low luminosity, which evolved in low redshift and high luminosity objects, the last step before to become companion galaxies. The large clump of high redshift quasars of the NGC 598 are bright in apparent magnitude, possible only if they are as close to us in space as the NGC 598 inside the local group. Inside the sculptor group, clearly visible from the local group, we have 2 big dominant galaxies, NGC 300 and NGC 55. You can deduce the position in the sky with respect to the local group from 2 parameters. The elongated distribution of quasars emerging from the first major galaxy, NGC 300, is half longer than the line in the NGC 598. The quasars around the NGC 300 are 1.5 fainter in magnitude than the NGC 598. It means that the apparent brightness of the quasars supports the fact that the galaxies in the sculptor group are about twice distant with respect to the NGC 598 of the local group. We can finally state that quasars are associated to galaxies ejected along lines in the nearby environment. The redshift cannot be due to recession velocity and does not indicate distance. The intrinsic luminosity of a quasar depends on its redshift, and at any given redshift, its apparent magnitude depends on its distance. The galaxy 3C120 is a strong radio source with broad emission line shifted to red by about 10,000 km per second, expressed in the redshift as a velocity, and the small radio features inside appear to be expanding 6 times the velocity of light, if the object was really at its redshift distance. The picture shows a galaxy with radio emission superposed. A relativistic jet ejects material directly in our direction, giving the illusion of an expansion faster than light. The galaxy is in the sky position of NGC 598, as previously seen, and if we observe the clustering of radio quasars with redshift bigger than 1.35, third circles, and hydrogen clouds, open contours, in the vicinity of the galaxy 3C120, the cross in the middle, the kind of associations and position predict that the galaxy 3C120 is a member of the local group, not at its given redshift distance. BL-like objects are active galactic nucleus and strong radio and X-ray emitter, very similar to quasars, at redshifts intermediate between quasars and cluster galaxies. By the action of ejecting material in opposite directions, they reduce their redshift. In the image, we can clearly see the ejections of material. These objects will generate a cluster of small galaxies having more material. The companion galaxies get normally attracted from the parent galaxies till they collide. The Seyfert NGC 3516 fulfills all requirements of new matter expelled from an active nucleus. It shows 5 quasars plus a BL-like type object having the lowest redshift at the most distance and nearer quasars having higher redshift. The apparent magnitude increases as the quasars travel outward from the core. The alignment of quasars is centered on a minor axis with a cone of about ± 20 degrees. The Fornaz cluster shows the NGC 1097, having the most extensive low brightness optical jets with a concentration of quasars as proof ejection from the nucleus. It's a quasar factory and it's possible to identify a BL-like object on the southwest line pointing to the galaxy. The radio and X-ray emission occurs both asymmetrically, making clear that we have 4 different ejections. The common denominator is the source of ejection, the core of the galaxy. The pictures shows the galaxy in light of hydrogen emission. It's possible to recognize the physical effects of the jets pushing against the spiral arms, with a consequent disruption of the galaxy. As we know the rotation velocity of the galaxy and the trace left in space, we can estimate when the ejection event happened. It was about 10 million years ago, a short time on the scale of the universe, but a long time for the humankind. A plot of all quasars on a large field around the galaxy NGC 1097 is shown in the picture. It corresponds to an overdensity of quasars by a factor of 25, compared to the expected background value. At the edges of the field, the quasar density drops to the average value in the sky. Deliberately looking for hydrogen toward the center of the local group, we found them near the NGC 598. The arrows indicate the distribution of quasars rotated only about 20 degrees from the line of hydrogen, possibly associated to the NGC 598, from which were ejected. The redshift's detection of the hydrogen clouds varies between -150 and -50 km per second, if we express the redshift as velocity. We can similarly observe a tail of hydrogen close to the NGC 300, another spiral galaxy in the local group. In this case, the line of quasars is rotated 25 degrees from the hydrogen line, which reaches 3 degrees in length and 4 degrees far away from the galaxy, whereas the cloud of hydrogen coming from the GC 598 reaches 6 degrees in length and 8 degrees from the galaxy. But as NGC 300 is about twice as far from us as NGC 598, and as angular scales are inversely proportional to the distance to the galaxies, therefore the two clouds have the same size and extent. The observations imply that hydrogen is ejected from the galaxies in an open angle as a result of the ejection of the quasars, holding a so-called smoking gun effect. We should expect a high redshift as big as for the quasars, but as the hydrogen is a primordial material extremely old in age, it can perhaps even have an intrinsic negative redshift. It might already exist in the outer region of the galaxy and be simply pushed out with the outward progress of the quasar ejections. Arp computed the probability of finding by accident a quasar at a certain distance from the galaxy, by knowing the densities with which quasars are distributed over the sky. The premise is based on the cosmological assumption that quasars with various redshifts must be on the sky uniformly distributed. A particular favorable configuration consists in a large spiral galaxy associated to a companion galaxy. There is strong evidence of quasars in spatial proximity of bright companion galaxies. The density of quasars at all different magnitudes around companion galaxies exceeds more than 20 times the measured density away from such galaxies. With the advent of X-ray and gamma-ray observations, hard energy jets and connections were found from lower galaxies to high redshift quasars, or between galaxies with different characteristics. It's the decisive way to establish their non-velocity character. X-ray sources are important because are often associated with quasars after spectroscopical analysis. Spectroscopically, a quasar looks like a small portion of an active Seyfert-like nucleus being found with similar physical conditions. Quasars are energized condensations of matter recently ejected from active galaxy nuclei. They show X-ray emissions associated to an energetic state of matter. Since the energetic X-ray tends to decay, it is natural to suppose that it should be indicative of younger jets ejected recently and hence higher redshifts. X-ray connections between dominant galaxy and quasars are found, but gamma-ray maps confirm strongly these connections, supporting the ejection of protoquasars material from active nuclei of older galaxies. It's a trio of interacting galaxies. The first two to the north are in an advanced stage of merging. A clear bridge connects the first entity with the second galaxy below. The spiral galaxy NGC 5297 with the companion galaxy NGC 5296 are connected by a luminous connection that terminates on a quasar. I'm showing you other galaxies without saying anything about them. Only one question: what do you see in the pictures? Most of all astronomers see the peculiarity of two neighbor galaxies by falling to each other, ignoring the evidence of ejections. If the colliding would be true, then we would expect to measure similar redshifts in emerging galaxies, and would fall together not straightforward but in a parabolic encounter. At final stage, when the companion galaxy smaller in dimension is old enough, then we can notice the merging process with the bigger parent galaxy. The merging is the last stage of the ejection and developing process of a quasar that has become a small galaxy. Any ejection from an active galaxy nucleus would stretch out its magnetic field, causing the rotation of the galaxy. The motion generates spiral arms, which become location of new star formation. Stephan's quintet is the most group of interacting galaxies all having different redshifts. The lowest object is NGC 7320, which has a redshift of 800 km per second, versus, respectively, 5700 and 6700 km per second that belong to the remaining galaxies. Important measurements reveal the existence of a radio emission between a parent bigger galaxy, NGC 7731, and the Stephan's Quintet. We can imagine an active galaxy nucleus like a plant maturing seed and then scattering them to its surroundings. Gemation is a term borrowed from the botanic, meaning the outgrowth of companions on the ends of galaxy arms. Definition from Wikipedia is a sexual reproduction in which a new organism originates as a localized area of growth on or within the parent and then differentiates into a new individual. The universe we live in is dominated by groups of galaxies, each dominated by one or two main galaxies. The rest are smaller companions with excess redshift. Objects with excess redshift occur especially in or along spiral galaxies. It is what we observe with the telescope, and I'm going to show you other examples. NGC 4151 is an active nucleus surrounded by smaller galaxies with high redshift. We can see the same objects as taken from Halton Arp after a deep exposure. NGC 1232 with redshift 0.005 has a companion on the left redshifted 0.02, line off the end of one arm, having the same resolution of the parent galaxy. Following its arm back to the center, we can identify the channel along which the companion could have traveled. Furthermore, there is an object perturbing the arm on the upper side, having a redshift fast 1/10 the velocity of light. It cannot be a background object, as it would be really difficult to see it through the disk of the galaxy, and one would expect a background object in red, but it is extremely blue. The redshift is the displacement of spectral lines towards longer wavelength, either in the visible spectrum or in other frequency fields, not visible at a human eyes. The electromagnetic radiation is a continuum spectrum generated from a light source. The redshift phenomenon is believed to be caused by Doppler effects when the source is moving away from us, by the expansion of space itself according to the Big Bang theory, or by an intrinsic characteristic according to Halton Arp. In the picture are represented absorption lines in the visible spectrum, which are produced when a gas is between the source of electromagnetic radiation and the observer. Each absorption line occurs when an electron jumps from a lower state to a higher state, extracting the required photon. It appears dark and corresponds to a specific wavelength associated to an atom or molecule, also defining the substances forming the gas placed in between. By getting the spectrum of galactic objects, we can recognize all the elements through which the light travels. Emission lines are produced when an electron falls back to a lower energy state, emitting a photon at a specific wavelength, visible in the dark spectrum. In this case as well, each emission line identifies a specific atom or molecule of the substances forming the gas. Quasars are ordered in redshift, with the highest redshifts closest to the galaxy and the lowest ones far apart. For instance, let's observe the quasar PKS 1327-206 with redshift 1.17, with a luminous filament connecting to the galaxy ISO 1327-206 with redshift 0.018. The spiral galaxy NGC 598, known as Triangulum Galaxy, is the third largest member of the local group, after the Milky Way and Andromeda. It has an interesting pair of quasars, 3C48 with redshift 0.368 and Parks 123 plus 25, a strong radio source with an extreme high redshift 2.353 and a very bright apparent magnitude. Because of the quasar's development process, we know that high redshift quasars are less luminous than the lower ones, because they grew up in matter. This leads to the result that the quasar Parks 123 plus 25 has to be inside the local group, as its luminosity is too high, because observed on north side instead on the background. Moreover, this quasar is probably a secondary ejection of the mentioned parent galaxy, as the redshift differentiates from the quasar 3C48. Therefore, we can state that normally quasars with redshift greater than 1.8 having high luminosity are not seen much beyond the local group. We have to decide if we are at the center of an expanding universe, if the redshift is an indicator of the distance, with us at the center, or if there is a same age and evolutionary stage distributed along a static volume, at different distances from us. Redshifts tend to fall near preferred quantized values. Quasars fit redshift patterns, or rather transition states between high and low energetic states. Starting with Geoffrey and Margaret Burbage, Carlson discovered that the redshift of the quasars obeyed the empirical law as shown here, thus forming a series representing the intrinsic redshift values. Observed values vary with the tolerance of ±0.1, which is thought to be the Doppler velocity component. The quantization peaks depend on the detail of quasars' evolution and might be seen such as a resonance state. The distribution of redshifts of quasars associated with a low redshift galaxy are shown in the following diagram. The peaks predicted from the formula are marked. Quasars are ejected in pairs equal spaced. It implies they were ejected simultaneously with equal velocities. Nevertheless, one of the quasars should have a component of velocity away from the observer, and the other toward the observer. In order to find the redshift of quasars in the reference frame of the ejecting galaxy, one needs to divide by the redshift of the galaxy. The value of redshift related to the velocity of ejection is given by the difference between redshift in reference frame of ejecting galaxy and the nearest peak in redshift. We can then determine the intrinsic redshift related to the age of the object, according to the general formula shown here. If the quasars were not associated with the galaxy, the correction will not move into the peak. If it does, it is evidence for physical association between galaxy and quasar. A conventional redshift distance interpretation of the quantized redshifts would lead to a universe of concentric shells centered on our galaxy. The alternative proposed interpretation is the redshift as measure of evolutionary stage of the galaxy. If we plot 260 galaxies from more than 80 different groups and we measure the redshift with respect to the central galaxy, we obtain this diagram. We can notice that the companions are the most positively redshifted and quantized in values of 72 km per second. The quantization can be associated to the birth of the galaxies at the origin point where the material emerges out of the nuclei, and the quantization itself establishes the non-velocity meaning of the redshifts. We could restrict the previous diagram to the M31 group represented by fair circles, and to the M81 group represented by open circles. We get for both galaxies essentially the same normal distribution centered at the value 72.4 km per second, with an error of ±2 km per second with a standard deviation of 17 km per second. An almost motionless value for galaxies interacting due to gravitation. Only when they get close together, their orbital velocities increase and delay the quantized redshift steps. Distances are independent of redshift, and we can establish the presence of non-velocity redshifts. The lowest redshift objects tend to be observed more distant and higher redshift objects closer to the galaxy of origin. This is expected if the intrinsic redshift diminishes as a function of the age, because the more distant ones would have been traveling longer. A student of Fred Hoyle giant narcular calculated a solution of the general relativistic field equations using mass particles as function of time, in order to account for intrinsic redshifts of the objects of various ages associated with an active galaxy. In detail, the mass of the particles vary as the square of their age. Since the redshift varies inversely as the mass, we have a relation between age of the particle and its redshift. We can notice in the diagram that the supergiant stars are 3 million years old in human time, and as the supergiant have the biggest brightness, it turns out that when we look at the most luminous stars in the galaxy, we will see the stars made of youngest matter. In fact, the evolutionary tracks of the brightest stars evolve away from the main sequence, instead to follow the reduction of the luminosity. This proposal requires initial ejection of plasma or low mass near light velocity. Since the initial mass is near zero, the initial state would be almost pure energy. Zero mass plasma particles come out with a signal velocity c, speed of light, and gain mass combining with atoms. In order to conserve momentum, they slow their translational velocity and reduce their temperature, generating the first event of a self-gravitating object. As galaxies have magnetic fields, the low-mass particles would then be guided out along these channels. In spiral galaxies, magnetic fields lie along the arms, and this leads to the suggestion that spiral arms are actually ejection tracts from active nuclei along which stars are being condensed or rather created. The spiral arms are the result of quasars ejection in an active galaxy nucleus. For this class of galaxies, higher redshift companions are to be found attached to the end of spiral arms. The largest galaxy has the lowest redshift and old stars. The smaller companion has higher redshifts and higher percentage of younger stars. If we consider the two biggest galaxies inside our local group M31 and M81, all companion galaxies are shown to be all of higher redshift. It is not a coincidence in an optic of an intrinsic redshift instead of recession velocities. The smaller galaxies are systematically redshifted respect to the larger. If we plot the excess of redshift of the companions compared to the biggest galaxies in the local group as function of their morphological type, it turns out that all companions are spiral galaxies, right side of the diagram, or namely young bright stars recently formed. The galaxy M31 or Andromeda is negative redshifted. Corrected from solar motion, the shift is minus 86 km per second. It means the galaxy is probably older than any other galaxy in our local group, and we originated from it. In fact, we are looking at our parent. Because of that, we see Andromeda as blue shifted as much as the redshift of the Milky Way seen from the point of view of Andromeda. Another demonstration of the intrinsic redshift is given by the measure of the distribution of the redshift of the companions with respect to the dominant Andromeda galaxy. According to the expansion model, we would expect other companions of Andromeda with blue shift. Instead, we measure only positive relative redshifts. It means they are younger objects and were ejected from the old Andromeda galaxy, just like the Milky Way. If we observe the pie diagram of the galaxies in the Virgo cluster, plotted by brightness and by redshift, symbol size decreases with decreasing parent brightness, the plot is telling us that the brighter the galaxy, the lower the redshift. Intrinsic has a low mass having a big amount of energy, and the fainter the galaxy, the higher is the redshift, associated to spiral galaxies identified by crosses in the diagram. Since we know that the central larger galaxies have the lowest intrinsic redshift, we should properly represent the distribution of parent galaxies along the space. It is the approach if the redshift is proportional to recession velocity and to distance accordingly. Instead, in the other graph, taking as basis the intrinsic redshift as function of the brightness, we see a complete other picture in the sky. Moreover, Halton Arp calculated the redshifts of the supergiant stars in the Small and Large Magellanic Cloud, members of the local group, corrected for negative velocity of stellar winds, or rather a flow of mass loss coming toward to us. It turns out that all supergiant stars are positively redshifted. It can be interpreted as intrinsic redshift, function of the stellar age, and not as recession velocity meant as stars running away from us, as it's known that in the local group the expansion of space doesn't apply. The higher redshift of the brightest stars respect to our position is named K effect, and is been thought from Halton Arp to be intrinsic associated to the younger age of the stars. The mass loss correction makes this excess in redshift even bigger. The picture resumes two different approaches of the general relativistic field equation. On the left, the Big Bang model with the mass of particle constant in expanding space that started from a singularity. whose redshift represents the cosmic expansion of space plus contributes of the Doppler effect. The result of the approximation made by Friedman leads to a model of curved space-time, an empirical artifact with no relation to real physics. On the right, the variable mass model based on the mass of the particles, function of the time in a non-expanding Euclidean universe, showing creation events from the existing matter. Objects are continually being born and are different in each generation. It's the narcular solution leading to a flat space-time. By putting the variable mass as initial condition from the general relativity field equations, it turns out that the redshift varies inversely with the square of the distance. Therefore, the cosmological redshift means seen matter creation at earlier epochs. The Hubble constant is indeterminate in cosmology, as the scientists introduced dark energy and dark matter to recover the discrepancies with the measurements. We can state that if Hubble had been discovered the quasars first and afterwards the galaxies, we would not have today an expanding universe. The current Hubble constant at around 70 km per second per megaparsec, supposed to represent the expansion velocity of the universe, leads to an age of the universe younger than the age of the oldest star in the galaxy. The variable mass theory has no adjustable constants because the Hubble value depends on the age of the stars. If we plot the redshift versus the apparent brightness for different galactic objects, there is the clear illusion that redshift increases as brightness decreases. The line would represent that proportionality, assuming the nearest galaxy Andromeda M31 as our reference. It shows how M31 would appear at greater distances from us. The line does not match with quasars and with the so-called extragalactic region too, consisting of almost stellar objects completely ignored in the Hubble law. Ignored because there are young matter, a connection between high redshift quasars and low redshift companion galaxies. An active researcher, David Russell, applied the redshift distances determined through the Hubble law to the rotational distance criteria and calculated extremely large diameters for the involved galaxies. It means something is wrong with these extremely large redshift values, and the redshift has an intrinsic component instead of a cosmological one. Many objects, previously believed to be at great distances, are actually much closer. The class of objects, such as the quasars, compared to the normal galaxies, violate the slope of the Hubble diagram, redshift versus apparent magnitude. Looking at the diagram, and particularly at the triangles representing the quasars far away from the dashed proportional line, the violation is clear. The quasars don't obey the assumption of same luminosity in an expanding universe. In the Hubble constant, there is no effect left over to be interpreted as distance velocity. It means the universe is not expanding and there is no need of the dark matter. The Hubble diagram roughly exchanges intrinsic redshift for recessing velocities. The intrinsic redshift varies inversely with the particle mass, and the luminosity increased inversely as the square of the intrinsic redshift. Seyfert galaxies are really important because have brilliant nuclei which emit a large amount of energy, being till to 100 times more luminous than the normal galaxies. This amount of energy has an excess of X-ray confirmed to be as quasar-like objects. Therefore, Seyfert galaxies are physically associated with quasars. Looking at the diagram, X-ray intensity on the x-axis is plotted against the apparent magnitude of barred spiral galaxies, with arms more widely spread emerging from the nucleus, and against the cumulative numbers of X-ray sources per square degree. Dashed line represents counts in non-Seyfert contour fields. Crosses represent the high luminosity barred spiral galaxies. It turns out that the barred spiral galaxies follow very well the excess numbers of X-ray sources associated with the Seyferts from which they were originated, in turn associated with the quasars, which show the same number count behavior with apparent magnitude. This kind of diagrams become the only statistical method of measuring extragalactic distances if the redshifts are not velocities. The theory of mass of oil and nuclear had its origin in Mach's principle, according to which a born electron has zero mass. As time goes on, it receives more signal at the speed of light from the rest of the universe, growing up in mass. The bigger the mass of the electron, the stronger is the light photon emitted in the transition. Therefore, the stronger is the change in wavelength, namely the redshift in the spectrum. The intrinsic redshift is not strictly related to a new creation of matter, but merely to a materialization of mass energy from a different location in the cosmos. In the core of a galaxy, the gravity can be so intense that a black hole has been theorized. Its salient property is that anything that falls into it can never come out. The observations show the contrary. Everything falls out of the core, from what we define a white hole. Because at the core, we would get a singularity having mathematical and physical inconsistencies, so that the matter can only get spit out of it. The matter comes out into our universe from a previously energetic state and not from nothing. For instance, we can see a video concerning the possible behavior of a galaxy inspired from a firework. Little bangs scattered throughout the space is what we observe with a telescope instead of a big bang, since we can never observe events at the initial moment. As the mass grows, the frequency increases. Therefore, looking out at younger galaxies, we are seeing them in an age where their clock were running slower. Time itself would be in a way as the redshift quantized. If particle masses are function of time, when a low electron makes a transition between atomic orbits, the photon involved has a lower energy and the spectral line is redshifted. Any older external observer will see the time of younger matter running more slowly, or rather redshifted. As time goes on, the particle masses exchange signals with other matter and their clocks asymptotically approach the same rate. From its reference frame, the universe is not expanding, but matter is intermittently materialized into it, with clocks that appear to run very slowly at first, to evolve then to normal rates. The time dilation for objects receding at high velocity, according to the special theory of relativity, is exactly the same function of redshift as for stationary objects whose redshifts are caused by younger creation epochs. The cosmic background radiation could be indicative of low temperature from weak photons all around us, and not from the background space.
Our entire view of the universe, the size and the mass and the contents, depends on this assumption that we can tell distances by redshift. If that one crucial assumption is incorrect, then our picture falls apart and we don't know very much. So that if you see objects which are clustered together or are interacting together, you know that they're at the same distance. And if you find that their redshifts are much different, then you know that the redshift can't be a measure of distance. We have galaxies themselves of different redshift, which are clearly interacting, but have much different redshift. This is a famous example of one of these. There are many like this known now. Big dominant galaxies and companions around them, which have the slightly higher redshift and increasingly higher redshift, but are all located in the same region of space. This visual shows that the biggest galaxy in each group is the SB, M31, and M81. And now all the rest of the companions, which everyone has always accepted as being companions, have systematically higher redshift. The only possibility is that there is an accidental projection of background objects. However, these objects fall so close that the probability is overwhelmingly that they are in fact associated. One of the objects we just saw, the chances was 1 in a million for an accidental association. Another object we just saw, the chances were 1 in 50,000. I think that that there's a great commitment to the assumption that redshifts always mean velocity. And there's a great reluctance to give up this assumption because a lot of work has been based on it. and there is this reluctance to recognize evidence which contradicts this assumption. However, if it's true that the redshifts are not always indicative of velocity, and it's continued to be believed that it is, if this assumption is continued to be believed, then we reach a very critical point in the science of extragalactic astronomy. And this is so important that I think that everybody, every person then has to make up his own mind, exercise his own judgment on this matter, and therefore I think it's very important to discuss the facts of the matter as we have here. My particular hypothesis, my working hypothesis, my explanation is that the matter which goes into making up these quasars and these higher redshift galaxies is young matter which has intrinsically high redshift, which is ejected from the galaxy and which decays and evolves as a function of time into more normal lower redshift galaxies. Inflation theory is the attempt of physicists to explain the expanding universe by means of fundamental physics, and in that process they conceive of creation of matter. The technical term they use is fluctuations in the material vacuum, and essentially you're looking at a piece of space and the properties vary and suddenly some material appears. My hunch is that the material appears where material previously exists in the center nuclei of galaxies, and that then this material flows out along the bridges or perhaps along the spiral arms.